Hello everyone and welcome to this session. So we have Josh Beatty here on stage and we have his adoring fans in the front row. If you guys want to give him a whoop.
Way!
Thank you. So Josh is here today to talk about Ctrl and F for missing people, exploring tech in the SAR field. So yeah, Josh, if you want to take it away.
Cool, thank you. So yeah, thanks everyone who has come out today. I didn't expect to be presenting on the main stage, so I was anticipating one of the smaller rooms. But yeah, so just to set things off in motion, we're talking about SAR, which is search and rescue, just for people who are unaware of the definition. But yeah, just before we begin, so I'm doing this talk for my own personal interest in the subject. Today I'm not here representing my company or any organizations that I'm with. All the information that I talk about in today's talk will be available online, and there'll be a QR code link at the end as well if you want to check out a link tree that has a bunch of references and further reading, a couple other links. And the final thing is I just want to talk about this to bring a bit of awareness for the subject. It's a subject that's probably not talked about, I would say, maybe enough. And yeah, find it like just a content warning as well. There's nothing in today's talk that's going to be like triggering, but just if you're affected by this kind of stuff or mental health, just to have a wee rain check. But yeah, so just to introduce myself. My name is Josh. I'm a full-stack software engineer. I've graduated from Queen's University in 2023, which is about 2.5 years ago now. And up until recently, I've been working for a software company doing software for fire, EMS agencies, and hospitals. My interests outside of tech, I'm a search and rescue technician for a local SAR team. And yeah, I've got interests in like hiking, healthcare, rescue, emergency care, coding, of course. So that's just a little bit about me. To give you an overview of what we'll talk today about, I'll start with a bit of an introduction to the world of search and rescue, give you a bit of background and context. From there, we'll dive into lost person behaviour, which is statistical data that we look at when we're trying to locate a missing person. I'll touch briefly on some of the challenges faced by SAR personnel on the field, just around technology, which kind of led on to an idea for a proof of concept app. I'll demo that, and then we'll wrap up with just some ideas for future improvements that I've heard from myself and stuff that I've had myself. So, someone is reported missing in the UK every 90 seconds. That's 170,000 people are reported missing every year. 96,000 adults and nearly 75,000 children. Some of these incidents are the same people multiple times, some of them are false flags, but in general, you're looking at 350,000 reported missing incidents every year, and that's in the UK alone. So, this is when search and rescue comes in, when someone goes missing. People go missing for different reasons. Your most common one is your lost person, an overdue hiker, somebody who's gone out, just lost their bearings in the nature, and or a lost child. People can go missing voluntarily, so every adult has a right to go missing. You're not breaking any laws by walking away from society, but police will want to find you to ensure your safety. Missing due to accident, injury, and illness is another big common one. That's things like broken legs or an injury, illnesses as well, so things like dementia. And a fourth one is missing under influence of a third party. So that's more complex scenarios like abductions and murders. There's a bit more complexity involved in those situations. So why is search an emergency? Like fire, like police, like EMS, search is considered an emergency because the MISPER's life may be in danger. They may require urgent medical care. Another thing is time and weather. Time and weather destroys clues. Dropped items, footprints disappear in time. A quick response greatly limits the search area. So from a person's last known position, there is a limit, there's a physical limit to how far that person can travel in that time. And the sooner we get started on the search, the better we can focus our resources. And then the fourth thing, going back to the person's safety, depending on their psychological state, a MISPER may be a danger to themselves as well. All in all, it is what to say, time is essential. To give you a bit of a context on what a search and rescue technician is, the roles kind of varied. At the baseline, all ground search and rescue teams are trained in a couple of things. That's comms and radio, casualty care and first aid, so that's things like for ourselves, for our team, for the missing person, for the general public. Everyone will be water aware, so we can work in and around water. Although some people will be trained to work in things like swift water, flood water, a couple of different disciplines. Search skills, that's things like search patterns, clue awareness, object detection, and of course navigation. Since we're out in nature, we need to be able to navigate ourselves. So that's using a combination of manual maps and digital mapping. One we'll talk about today is an application called CalTopo. I don't know if anyone has been on hikes and has used that software themselves, but it's really good. And I'll show you that in a bit. And just kind of to round out the context, going from the boots on the ground type stuff up to a higher level. When a person goes missing, they'll be reported missing. A risk assessment will be done for that missing person. That might launch a police investigation, and then at that point, search and rescue teams will be alerted, put on standby, and tasked. And at that stage, the search mission commences. It all mostly follows the same cycle. Search team is alerted, so that's by ways of the police contacting us or a family member of the affected family reaching out directly. We'll do search planning. So once it's approved, a search planner and a search ops lead will use the available information to draw up a search plan. That'll be things like the description of the person, the last known position, the last time that they were seen, what they were doing at the time. But to start a search, all we need is the last known position of a person. From there, we can just go and start looking for people who might need help. But yeah, then the team is briefed. We use a SMEAC format, so that's situation, mission, execution, admin, and command. It's just a way that we format briefing each team member. We execute the plan, hopefully with the mission of recovering the casualty to a safe place, and do a debrief after. So, as we've discussed, there's quite a lot of things that can affect a search. We're talking the terrain, the climate, the subject themselves, so like their physical condition, how much can they move, the psychological state as well. If the person is intoxicated, if the person is despondent or has depression, time since the person was last seen, and the resources available. Also, like all these factors will affect how a search is carried out. And in search and rescue, because of all these variables, there is a Bible, and that Bible is a book called Lost Person Behaviour. It's a book that's written by a guy called Dr. Robert J. Cuesta. It's essentially an indispensable guide to finding lost people. It contains the latest search and rescue incident statistics in the form of a database that's called ISRID, and that's International Search and Rescue incident database. And that itself, it contains over 50,000 search and rescue incidents and all the data associated with it. It's divided up into 41 subject categories. That's broken down into things like abductions, children age groups, outdoor activities, water-based scenarios, mental states. And all that data is presented in a couple of different ways. It's presented with different statistical models. There's specific data as well for terrains and climates. And I forgot to show it, but that's the book there. A lot of people carry a manual guide. So yeah, I mentioned it's presented in a couple of different statistical models. To just name them really quick, there's a displacement model, so that's the horizontal distance from their last known position. Dispersion, which is if we know the direction that the person has gone in, what's the likeliness that they're along that line of direction. Elevation, it is what it is. You know, it's the probability of a person going uphill and downhill. In the past, it was mostly downhill, but in recent decades, that's switched to being more uphill because people try to get better phone signal. Track offset, which is how far off the path a person might be. Very different if it's like a biking accident to a dementia person who might tend to wander off a path. And then the final one is more complex. It's the watershed model. That's how a casual team might behave in relation to the flow of water. But we'll mostly just be talking about the displacement model today, which is the most basic one. It's the distance from the last known position. What does this look like then when we draw it on a map? So we use something called the reflex model or the bike wheel model. It's used by most search and rescue teams. It consists of 5 things. We've got an initial planning point, which is the very center of the bike wheel. Around that, we have a hub, which is usually a 300-meter circle. And that's the location of the highest probability of finding that person. You have the spokes, which are the paths that lead away from the last known position. The rim is the outer bound of the search plan, and that can expand over time. And the final thing is reflectors. So that's areas of interest that a person might be drawn to. That could be their house, public places, a pond, a lake, things that might attract attention to the person. So I've rambled enough there. Let's see what this looks like when we draw it on a map. So props to anyone who recognizes this on the satellite view. This is Black Mountain. This is up near Cave Hill. I'll walk through what this looks like when we draw it on a map. So we've got the initial planning point. We've got a John Doe who was last seen at 1 o'clock today, and he was out hiking. So we'll start from that last position. We'll draw our rim, which is the outer bounds of our search area. We'll use the 50% ring. So that data that I'm talking about is given in 25% chance rings, 50%, 75%, up to 95. So that's kind of what that looks like. From there, we'll go back and focus in on the IPP. So here is pretty basic. We'll just divide the area around our center point into a couple of search zones. So we've got a weather station, and there's a mountain trail to the north, which has a field, and below that, there's a boardwalk as well, which we can also divide nicely into another field. From that, we'll then draw the spokes. So that's all the paths leading away from that last known position. We'll aim to probably do like a hasty search and route path along those. And then finally, we'll just draw in the reflectors, which aren't too many in this area, but that's things like a radio station to the north. There's an observation area to the east. To the west, there's a visitor car park and a coffee shop. And I think that's it for that area. Yeah, so that's kind of what that would look like if we drew it up on the map. Now, that all takes time. There's a couple of pain points when it comes to drawing up a search plan. This is a photo from a recent training thing that we did a couple of weeks ago. It essentially shows a search planner who is briefing all the team leaders, who will then, after they've been briefed, they'll brief their individual teams. There's a lot of chaos that's going on out of focus. Organized chaos, I would say. People grabbing equipment, people getting their dogs ready to go out in a search. And just in the very back there, you can see me, who's frantically trying to draw up a Caltopo map to assign these search team leaders to go and commence a search. So it is what to say. Like I said it before, time is of the essence. That's our biggest factor. The fastest that we can organize a planned search, the higher chance we have of finding that person. And then obviously working in the field as well. We've got limited technology, so our search techs usually only have their phones. The person in the command vehicle might have a laptop, but even though we have these devices, it's a very low to no internet environment most of the time. So with these constraints in mind, it's kind of led me on to just explore the idea of a proof of concept app just to help reduce time in that search planning phase. The aims that I set out to do for myself was to reduce the time spent in the search planning phase. It needs to be something that's easy to use in the field, work in a low to no internet environment. Ideally, lightweight, optimized, something that can be ran locally on a mobile device. No heavy algorithms or AI models that require internet connectivity. And the goal as well is to integrate with existing SAR tools. I'm not setting out to replace anything or replace boots on the ground effort. So that's sort of led on to me creating a search and rescue planning wizard. I've been calling it AutoSAR, but I'm trying to get away from that name because it's not too catchy. But yeah, AutoSAR, it aims to meet 4 objectives. The first is to create a mobile-first design to be used easily in the field. It needs to integrate with Lost Person Behaviour to assist in drawing up these search plans. Intelligent sector suggestions, that's nearly the meat and bones of this. There was a goal to see if we could use image processing techniques to automatically divide the hub, or at least suggest reasonable areas to divide that up into search areas. And then the final thing is offline mapping, so again, for low to no internet environments. The tech stack that I chose to use for this. So I have experience using Android Studio for final year projects, and I'm most at home in an Android-type environment. So I actually went with Kotlin and Jetpack Compose as my UI library. The reason I chose Kotlin over Java was mainly because it can integrate really well with Mapbox. Mapbox is a really easy to work with SDK that provides high quality satellite maps for Android, and it is also the library that Caltopo uses. So working really well together, we can export and import these objects from one application to another. And then the final thing as well, just for the image processing techniques, I've gone with OpenCV, basic bread and butter. I've used it before. I imagine many people have as well. So I will show you what this app looks like now. I have a quick recorded video, and I'll just walk through it. So this is me opening the app. It presents you with a satellite map, which gives you a couple of basic features. You can rotate it, zoom in on your GPS location. But we'll just go ahead and try and do a quick search here. So when you... Good call out. Yeah. So I'll run it back just a couple of seconds there so you can see. So this is the app here. It loads up, again, a couple of quick basic things. It has the ability to rotate the map. zoom in on your GPS location, and then if you long press on the crosshair, it opens up a quick dialog, which is all the subject categories that's in the Lost Person Behaviour book. We always aim to prioritize, never assume anything in a search. So you can select missing person might be applicable for multiple categories. So you can select multiple, so mental state and a child. And it will prioritize the one that will affect data the most. From that, we can select the terrain, so mountain or flat, the area type, so temperate, dry, and urban environments. And then that automatically draws those map features using the LPB data. So that's your IPP marker. We've got the RIM, which is the 25, 75, 25, 50, 75, and 95% quartiles. And then from there, again, the meat and the bones, there's a button to attempt to automatically sector the hub. I've tried a couple of different algorithms here, just again, mostly for like a proof of concept approach. And that's all done very quickly, using basic processing techniques. And then the final thing is we can export this in a GeoJSON format. At the moment, it just saves it to your downloads folder on your mobile device. And then you can very easily import that into CalTopo, which I think I show off here real quick. One other thing that carries over as well, so based off the subject category that you've picked and other variables in play, it'll give you a quick description of the circumstances in the IPP marker. So we're looking for a despondent person in a flat terrain in an urban environment. And yeah, essentially that just saves you a lot of time, creating all these map features manually, looking that up in the book. And I don't have it at the moment, but ideally you would carry over the sectors that it's suggested. And that's mainly it. Yeah, I'll jump back to the slides here just to talk a little bit more in depth about how I approached this. So yeah, like I said before, sectoring the hub was kind of the meat and bones of this project. I just wanted to explore how possible that is with a lightweight algorithm. My first approach was more manual, and it was leveraging my own experience with OpenCV from my final year project. I've got a very basic pipeline here. So we have a satellite image that we start with. We convert it to a matrix, apply a grayscale, a Gaussian blur, adaptive binary, a binary threshold, I think it was, morphological cleanup, contour detection, and then there's some custom algorithm to approximate polygons and then convert that to geospatial coordinates. That's the code for that. No one's going to read code here, but it's easier to show the results, which for the first approach, that's kind of what it is. Again, you can see the raw satellite that we started with. We've cropped it a wee bit to get rid of the Mapbox logo, blurred it, binary threshold, which you can still kind of see some of the features, morph cleanup, and then ended up with that mess. So that didn't work too well. So I took a second approach. Instead of edge-based segmentation, I tried a more region-based approach. And I admit this is more of a vibe code approach. I kind of ran out of time last week, so I gave it a shot. That process is more complex. We have, instead of immediately grayscaling it, we try to use RGB data, which instead of getting rid of that immediately, is quite handy to find an adaptive threshold between areas. Yeah, we do some pre-processing, so like applying a histogram equalization, flatten the image. K-means clustering as well, just to try and identify some of these sectors. Again, that's the code for it. You can find it on the source code, but easier to show this, which is sort of the output at each stage. Again, we're starting with a satellite image to begin with, applying a lab color space, the histogram equalization, K-means clustering, which isn't too much of a difference between that, converted to grayscale, blurred and morphed it, and then put another binary threshold over, and that's sort of given something a little bit promising. You can see that it's clearly identified some larger polygons and tried to draw bounds around it. But there's still a lot to be desired. The polygons need cleaned up and placed more accurately. But yeah, future ideas, final project, final points. Ideally, how I would sectorize this area might look something like this. So on the left is the output from the latest algorithm. On the right is somehow I might do this manually. You can see the IPP is the car park there, and we've divided it up into a couple of polygons. And you can kind of see some of the correlations between one image and the next. Other future ideas, ones that have been given to me by my team, are the SMEAC briefing notes part, which is just a wee pull box up and down. Again, when we do the search planning, we organize briefing notes in a sort of situation, mission, execution, admin and command approach. That would be really easy, just to add a long text field at the bottom and then carry that over like it was in the IPP market description and just have that there. Another great thing to implement as well would be tactical briefs. So the LPB book, it also has a tactical brief for each subject category. It contains useful information to be reminded on, things like circumstances, risks, reminders to keep in your brain, in your mind. And that type of information would influence the type of gear that we carry and the type of equipment on a search. And yeah, it's a very easy thing to add that to the IPP marker. And then some other future ideas, just a quick fire. So as well as LPB data, there's another database called iFind, which I think maybe the Coast Guard use sometimes. The current data for LPB is just a JSON file, so switching that out, configuration style, would be really easy. Mapbox has download region capability, so although the app is a very low internet, because all we need really is some satellite images, which is easy enough to get, we want to make it fully offline, so that's one option hopefully I aim to implement. Cloud storage, I know I said by no internet, but it is handy to save maps and sync them across devices. And again, thinking about multiple devices, I did this for Android. Some people use iOS, and then for the search planner on their laptop, it'd be really nice to have this on web as well. AI always gets thrown out there too, so auto-generative narratives for briefing notes is an idea to explore. And then finally, streamline the input to Caltopo process. So instead of just downloading a JSON folder, it'd be nice to like automatically streamline that transition to switch over to the next app. But yeah, that's it. I guess, point of why I'm doing this talk is just a call to action. I'd love to see more tech for good out there. There's plenty of problems still to be solved, especially in these types of systems. We use a lot of outdated, still manual processes. So yeah, just guys, get out there, start coding these projects. Look for that more impactful job. Take another week or two to look for it, and do more beyond the desk. And yeah, that's it. I have a link tree just with some of the references that I've used in today's slides. You can go ahead and scan that QR code if you want. And there's some further reading. And if you want to support the cause as well, there's a donation link to my local search and rescue team. But that's it. Thank you. Just about kept my voice there.
I know, you did well.
Yeah.
So thanks so much, Josh. We have time for a quick Q&A. Has anyone got any questions? And I'll run over. Perfect.
Thank you. Is this like a proprietary, closed source thing you're selling, or is this like an open source thing you want people to jump on board with?
Quick question. I've had that asked of me a lot. At the moment, it's just an open source code. On the link tree, there's a link to my GitHub repo if you want to have a look. It would be something that's handy that people would actually use, and I've used it myself in a lot of training situations. But yeah, I mean, go on with it. It's like that.
Anyone else have a question? Perfect.
So you were saying how, it's designed to save you a lot of time with having to manually draw out these search areas. How much time do you foresee in its final form it could actually save in a search and rescue operation?
It's a good question and something that's difficult to quantify. Some search plans, we're looking for people who've been gone missing for a long time. So there is that time to search plan. But quite often we'll get a call out and it's just we have to get to this location really quick. People will start showing up at random times. So there's a real race to get this map drawn up, get teams out in the field. Depending on your skill with CalTopo, some people aren't too familiar with it. It might take 15, 20 minutes. But in general, 5 to 10 minutes. It's just time saved, and that time is really felt in the immediate chaos of everyone showing up. I hope that answers your question.
It does indeed. So it'd be the kind of thing where you could set the algorithm to run, get in the car, go. By the time you get to the location, it's ready to rock and roll, and you can just do the briefing and get out there.
Yeah, and it also reduces human error as well,
Yeah.
because there's a lot of data being manually copied across from either book to app or app to app. So handy
Thank you.
from that regard. Yeah.
And I think that's all we have time for. I just want to say thank you to Josh, who has the empathy and intelligence to be able to merge the two together and make really useful things like this. So thank you.